Question number 3, is asking what is an augmented matrix? All right. An augmented matrix. So an augmented matrix is a matrix obtained by appending the columns of two given matrices. Sounds a little bit confusing, but we can see through an example, okay? So if we have an example of a system of linear equations, given as, for example, we have 2x plus 3y, 3y minus 4z is equal to 1. So this is the first equation that we're given. The second equation that we're given is x minus y plus 2z is equal to 2. And our third equation that we're given to is 3x minus y plus z is equal to 7. So in total, this creates a system of linear equations because each one of these are linear equations. So make sure when you're writing your system of linear equations that they are in the proper form, that we have all of the terms with x, y, and z on the left hand, or like on one side of it, and all of your knowns or constants on the other side. In this case, I have the unknowns on the left and the knowns on the right, but obviously you can choose whichever one, as long as each equation that you're given is formatted in the same way. Okay? We want all the x's to be lined up, all the y's to be lined up, and all the z's to be lined up. And then we can start to create our matrices. So from these 3 equations, we can create 2 different matrices. So typically when you're solving a system of linear equations, you want to solve by, I don't know, it doesn't really matter, but I usually see it like this. This is how you would solve the system of linear equations, though we're not trying to solve it. But this is the form that you have. So this is where your matrix A contains the coefficients of the unknown variables. And we have B, which contains the known values, or the constant or known values from the linear equations. And then X, although we're not going to be using it here, contains X, Y, and Z, usually in a column matrix, but we don't need to worry about that anyways for this question, but just for your reference. So we can compute or compile, I guess, matrices A and B using this system of linear equations that we're given, okay? So let's start with A. So A, like I said, is containing the coefficients of the unknown variables, okay? So we typically line it up so that we have equation, that's just shorthand for equation 1 here, 2 here, and 3 here, and by here I mean each row of this matrix contains those values, and as I said, they are the coefficients of the unknown variables. So that does not mean that I'll write the x and the y and the z. I'm writing it without the x, y, and z. So first column here, like I said, if I imagine I have, first row, first column. Imagine if I split it up into 3 different rows, one for each equation. The first row, I will have 2 3, well, I might as well write it like this too. We have x down the first column, y down the second column, and z down the third column. So now we're totally labeled. Okay, as I was saying, we have 2, 3, and -4. Now for this second equation, for x, we just have 1, since it's just x, so you can imagine an imaginary coefficient there of 1. The second one is -1, same thing, there is no coefficient there, but you can imagine a -1 out in front. And then we have +2. And then for the third column, we have equation 3, which is 3, -1, and +1. Okay? So hopefully with these labels, it's a little bit easier to see. We typically write these matrices without any separations, and these numbers kind of just sit there. So in order to scroll down, I'm just going to show you on the left-hand side here, we have the equations. I'm just going to scroll down so you can't see them anymore. So we can also compile matrix B, okay? So as I said, matrix B consists of the constants or known values from these equations that in this case are all found on the right-hand side of each equation. So this is a column vector or a matrix with only one column. So as you can see for equation 1, we have equation 2 and equation 3 again as each of the rows. For equation 1, we have the known or the constant of 1. For equation 2, we have the constant of 2. And for equation 3, we have 7. Okay? So now that we have both of our matrices, all we have to do is put it together. That's what an augmented matrix is. So let me label it. We have our augmented matrix. And that essentially is just A and B combined into one. So we'll draw the lines like this. So they're just straight lines. And in this first section, we will put our A right here. And our second section, we'll put our B. So just lined up like this. Okay, so our first section, we have our 2, 3, -4, 1, -1, 2, 3, -1, and 1. I'm just taking from up here. And so that's all A. Didn't really look like anything. So for B, remember we just said from here, we just said that B was 1, 2, and 7. And that's basically it. Make sure that for each, so you can see here that each column represents each equation. Make sure that it's properly lined up so that you have the proper terms. Make sure that, for example, it's not 2 and 1 in your B vector or your B matrix, because as you can see on this side here, that would be lined up with the wrong equation. The answer for this one was not equal to 2. So yes, make sure that everything is properly lined up. And you could see that, or you should see that the resulting augmented matrix mirrors the initial system of linear equations that you're given. And that's it for that question. Okay. Looking at the solution, we have the same thing here. Okay. So we can say correct solution. And move on.